you may be wondering what that was all about. Hello everybody, this is Matthew, and today on BrainSTEMs we are going to be talking about why math is so important in music. When you think of math, you probably think about the multiplication tables you had to memorize in 4th grade, or about the slope-intercept form of a linear equation. Though that is math, math has a more important role in anything and everything. Some of you may know how math is involved in art. For example, the golden ratio, which was discovered by the ancient Greeks and used in art and architecture. Though, the question I want to answer today is how music relates to math. Math and music may seem like completely different things, and studies have even shown that both topics use completely different sides of the brain. So, how does music relate to math? Well, for starters, most people know how musicians must continually use fractions, decimals, and percentages in rhythm. Rhythm is how we organize and follow musical patterns as they move through time. When composers create music, not only do they have to consider if the notes sound good together, but also the length of each note, how many beats per measure, the speed the notes are going at, etc. Rhythm is important in music because it is the driving force of the music, and it gives music a structure. A good rhythm in a piece is usually what makes it attractive to people, and usually complex or pleasing repetitive music draws people towards it. When you think about it, a lot of the songs you hear on the radio have a simple but fun and pleasing beat that's really easy to get stuck in your head. For example, different genres of music also has different emphasis in rhythm. For example, marching music usually has beats 1 and 3 emphasized, and rock music usually has beats 2 and 4 emphasized. Listen to When Johnny Comes Marching Home and Johnny Be Good. Deep down in Louisiana, close to New Orleans, way back up in... Can you hear the difference? Now, rhythm being associated with math is not that hard to see, but math is connected to music in many other surprising ways. Pythagoras, an ancient Greek philosopher most known for his famous Pythagorean theorem, made an important discovery in the mathematics of music. We know that when we pluck a taut string, demonstrated with the guitar, that it vibrates and produces a note, in this case E. Now, let's do it again, but divide it in half. With the measuring tape, you can see that from here, the length from here to here is 25 inches. And half of that is 12.5, right here. If I pluck over here, holding my finger down right here on half, if I pluck, according to the toner, it's E again, exactly an octave higher. An octave is a note that is 8 notes away from the original note that has the same sound. For example, from middle C, 1, 2, 3, 4, 5, 6, 7, 8. Another C. They sound exactly the same because they're an octave apart. Pythagoras didn't just stop with that discovery. He decided to see what would happen if the string was divided into 3 parts. This time, the note was different, but he realized that it combined well with the first note. This new note was 5 notes away from the first note. For example, C, 1, 2, 3, 4, 5, to G. Repeating this pattern over and over, like so, G, 1, 2, 3, 4, 5, to D. D, 1, 2, 3, 4, 5, to A. Created the circle of fifths, which is a tool used by musicians to show the relationship of the 12 notes of the chromatic scale. Pythagoras continued making these new notes and combining them, making the musical scales that we know today. Another interesting connection to math is each note's distance from each other. For example, let's say we have the C note, which has a frequency of 261.6 Hz. If we multiply 261.6 by the 12th root of 2, we get 277.2, which is the frequency of the C-sharp note, the note right next to the C note. And if we multiply 277.2 By the 12th root of 2, we get 293.6, which is the frequency of the D note, the note right next to C sharp, and so on and so forth. If we multiply the 12th root of 2 by itself 12 times, we get 2. And because there are 12 notes in the chromatic scale, multiplying the C frequency by 2 is just the C frequency again, but an octave higher. As we saw earlier with the string, where we divided it into 2 parts and it became an octave higher, a note's frequency multiplied by 2 is the same note an octave higher. Pretty fascinating, right? Now, let's move on to arguably the most mathematical musician of all time, Johann Sebastian Bach. Bach is known to many as the grandmaster of innovation and invention in music, and was known for his pieces with multiple melodic lines, with notes acting as both harmony and melody at the same time. Bach was also a master at symmetry. In both math and music, symmetry is a pattern where you can transform something and it will be the same. For example, a shape is symmetric if you can fold it in half and the sides line up perfectly on each other. Now, Bach loved to play with symmetry and was great at it. In his fugues especially, like the one you're hearing right now, he liked to repeat the same theme multiple times, but with a little variation, using different instruments, different speeds, different starting points, and sometimes flipping or reversing the same theme over and over. Bach was able to create entire musical pieces. Here's an animated visual representation of this. Well, you get it. I'll be posting a link to the original video in the description if you want to watch the entire video. Now, we see how almost every aspect of music is connected to math, and we can use this information and plug it into AI. Because math makes music predictable, AI, judging from the composer's works and style of music, can make songs by the composer. In 2019, a Chinese company teamed up with composer Lucas Cantor to complete the unfinished Symphony No. 8 by Schubert. The AI analyzed information about the timbre, pitch, and meter Schubert liked to use from other pieces and fed the composer ideas on how to finish the piece. On February 4th, 2019, the finished piece was performed. If you want to learn more about this, there's a link down in the description with more information. I also found a post where a programmer created a deep learning model that analyzed the sound file of different classical songs and predicted the composer based on the composer's music style. Again, I'll be posting a link to that down in the description if you want to learn more information about it. Music is intricately connected to math, and with more technological advancements, it is becoming more and more predictable. So that was a lot to cover, but the purpose of this video was to show you that math and music are not all that unrelated. This does not only apply to piano, guitar, but to pretty much every musical instrument. Great musicians of both the past and today may have great mathematical minds, and may even understand math better than the average person. Even though it may be hard to see how music, a form of art, and math is connected, I hope this video has given you a little more insight on both topics. If this video piqued your curiosity on the subject, and you want to learn more, consider taking music theory. This video barely touched the surface of math and music. And lastly, I want to thank you for watching this far in the video. My channel is still pretty new, and I'm still experimenting with different things. I've put in a lot of time and effort into making this video, and I want to keep making videos like this for you guys. I want to start a series called Mini Research Projects, where I research about interesting topics like this and show you my findings. If you have any suggestions for me, or you want to give me ideas for videos in the future, please comment down below. Also, kudos for my sister for playing the background music of this video. So, I hope you enjoyed the video, and if you did, please consider supporting the channel, as that would help me a lot. This is Matthew from BrainSTEMs. Thank you for watching. See you next time.